Okay, gang, new look. We're going to try something new today. I bought it's called a Ziggy HD. Uh, no, I don't know really what it's called, to be honest with you. But what it allows me to do, instead of writing on the blackboard on the dosery, it allows me to just take a piece of paper and project it onto the screen. There's going to be a lot of writing. There's going to be a lot of times that I'm going to need to use information from previous screens. So I thought that the blackboard may not be the most effective way to put this video up. So yeah, I don't know. Well, hey, we'll try it. And as I sit here, I feel like I almost feel like I know that I'm going to be doing this video like 15 times before it gets publishable. So this is the first time. So hopefully it works. What's getting ready to happen in 6500? A couple of things. We are going to explore more on multiple regression, and the next few issues or so that we're going to look at. First of all, we're going to explore what's called the extra sum of squares. And what this does, this is going to prove to be useful when conducting a variety of tests about our regression coefficients. Now, I suspect that this part is going to take this up here is kind of annoying, isn't it? This shadow, but I really don't know there's much I can do about it with my lighting. So guys, bear with me. And if this is just horrible, let me know and we'll change things up. But so anyway, the first thing we're going to look at is extra sum of squares. I'm assuming this is probably going to take somewhere about somewhere probably around 2 weeks. The next thing I want to look at is the standardized version of our multiple regression model. And next on the agenda is something we call multicollinearity. It's kind of like a supercalifragilisticexpialidocious term. And this is just nothing more than a condition when our predictors, and this would be quantitative predictors, are highly correlated. Now, this creates issues with matrix operations. What happens today, our statistical software packages are so powerful that they're pretty much able to kind of go right through those. Let me see if I can get a little bit closer where this is going to be a little larger. And again, guys, this is just a trial and error. I have no idea what's going to happen here. All right, so guys, first thing, again, this video is on this extra sum of squares. And the basic idea here is the following. I'm going to switch over to another sheet of paper. So the basic idea is the following. The extra sum of squares measures the marginal reduction in the error sum of squares when an additional predictor is added to the model. Now, and I should say this extra sum of squares measures the marginal reduction in the error sum of squares when an additional predictor is added to the model, given that there are existing predictors in the model. Guys, equivalently, we can say that one can view the extra sum of squares as the marginal increase, and I want to underline these. So as the extra sum of squares as the increase, and I should say marginal increase in the regression sum of squares. When an additional predictor is added to our model. And this should be really no surprise, considering that our sum of squares for our total can always be expressed as the sum of squares for our regression plus the sum of squares for the error. And this part up here just says that if we add an additional predictor into our model, that this will decrease. Well, think about it, that has to decrease, then the sum of squares for the regression would have to increase, at the same rate. So that should be fairly straightforward. Now, what I want to do, the last three videos dealt with a data set, a body fat. So let's re-examine this data set, and I've uploaded it to Blackboard, and it's available, I think, under week 6. But nevertheless, Y turned out to measure the amount of body fat. X1 was something called a trifold. It's not. I think it's like a tricep skin fold measure. Now, I really don't know how they do that. Apparently, they let you hold your arm, which you can't see me. Let you hold your arm and measure how much skin is hanging at the bottom of your tricep. I have no idea. X2 was a thigh circumference. And I'm pretty sure that X3 had something to do with like a forearm. I think they called that a mid-arm circumference. And guys, at the end of the day, the idea here is to measure body fat extremely expensive, so I've been told, and a very cumbersome process. And I think it includes dipping someone in water, and really, I'm not even going to sit here and act like I know how to measure body fat, because I don't. But I know that if we could come up with an easier way And you got to admit, even though I don't really know what this tricep skin fold measurement is, I'm sure it's easy to measure. Thigh circumference would be extremely easy to measure, and this mid-arm circumference would also be easy to measure. So if we could find a valid and reliable model that provides a good predictor of the person's body fat, then it would be much easier than the expensive and cumbersome process. Now, what I want to do here is I want to get into this data set, and I want to look at a few things. So I want to examine, I want to examine 4 things. So the first thing I want to look at is y just being predicted by x1. The second thing I want to look at is y just being predicted by x2. The third thing I want to look at is y being predicted by x1 and x2. And I'm running out of space here, so I'll put that right over here. The fourth thing I want to look at is y being predicted by x1, x2, and x3. So get the gist here. Now let's, I've already got R up and running. But I want to get organized here because we want to be able to very quickly look at our results and go from there. So let's create some new notation. So the first model, I've got y predicted by x1. So what I'd like to be able to do is I'd like to examine the sum of squares for the regression, having x1 in the model, and I'd like to examine the sum of squares for the error with x1 in the model. The next thing I'd like to do is examine when x2 is in the model, I think. Let me, I wish I kept better notes of this stuff. Well, shoot. I'm pretty sure it was x2, yeah. Okay. So what I'd like to be able to do here is I'd like to look at the sum of squares for the regression for x2 and sum of squares for the error for x2. The third model I want to examine is I want to examine the sum of squares for the regression and error when we put x1 and x2. So I'm going to have this as the sum of squares for r, x1 comma x2. And guys, finally I'm going to look at the full model. And I want to look at the sum of squares for the regression for x1, x2, x3, and then the sum of squares for the error for x1, x2, and x3. So guys, hopefully all that's clear. Nothing fancy. So guys, what I want to do now is I want to get out of this, and I want to go to R. And you'll see what I've done. I've already set my working directory, imported my data, attached it, and I really don't need to look at it. But I want to look at the name so I know how to type in things. So guys, the very first thing I'd like to do is I'd like to look at ANOVA, my linear model, where I predict body fat from triceps. And you can see here that my sum of squares for my model is 352.27. And my sum of squares for the error is 143.12. And I'm writing this stuff down as I go along. Next thing I'd like to do is look at the linear model for body fat. As it's predicted from x2, which would be the thigh measure. And you can see that my sum of squares for the regression is 381.97. And it's 113.42 for the sum of squares for the error term. Next thing I want to do is look at the linear model of body fat as it's predicted from x1 and x2. So that's going to be triceps plus thigh. So my error is going to be 109.95. And let's see, so we've got 352.27 plus, I can actually do that in my head, but I just want to make sure. So the regression sum of squares is 385.44. All right, gang, let's throw it all in there. I'm going to cheat a little bit here. Is that legal? And what I want to do here is just throw in mid-arm. All right, so my residual sum of square, I'm sorry, my error sum of squares went down to 98.40. And my regression sum of squares would be 352.27 plus 33.17 plus 11.55. So 396.99. All right, so nothing fancy. Now, let's go back to this. So you can see that I wrote everything down because I want to have it handy. And let's see if I can get things centered here. All right, guys. So what I want you to notice a couple of things. First of all, notice that the sum of squares for the error for x1 and x2 is 109.95. Second thing I want you to notice is the sum of squares when just x1 was in the model is 143.12. So the difference in I'm running out of room down here. The sum of squares for the error is called the extra sum of squares. Now, guys, this extra sum of squares that we looked at is denoted x2 given x1. So, and we can see that this is going to be equal to the sum of squares for x1 minus the sum of squares when x1 and x2 are in the model. So guys, the sum of squares for x1 was 143.12. The sum of squares reduced when we put both values in the model, x1 and x2, is 109.95. So we have a difference there of 33.17. What we're going to call this is we'll say that the reduction in the error sum of squares as a result of adding x2 to the regression model when x1 is already in the model. Equivalently, and guys, this goes back to the fact that when we add an extra term, we expect for the sum of squares error to be reduced. And we talked earlier that when we add an extra term, we expect for if we add a reduction in the sum squares for the error term, or sum squares for the error, then we should have an increase in the sum of squares for the regression. So we could also say that the sum of squares for regression of x2 given x1 in the model would be the sum of squares for the larger part, and this is again for the regression, minus the sum of squares for the smaller point, or smaller part, I'm sorry, where we just have x1 in the model. So guys, if we go back to our output, we can see, I should have written this down, but I didn't. Daggone it. Yeah, actually I did write this down. Okay, cool. So the sum of squares when both for the regression was 385.54. And the sum of squares regression when just x1 was in was 352.27. So guys, notice we get 33.17, which is equivalent to what we found before. Now, this should be no surprise, and the reason for this is the ANOVA identity. Which says that the sum of squares for the total is just the sum of the sum of squares for regression plus the sum of squares for the error. So it's kind of rob Peter to pay Paul, that kind of thing. If you take away from the sum of squares, then you have to add to the sum of squares for the regression. Okay, so at the end of the day, we can make a bold statement here. Nothing prophetic or anything, but we could say that any reduction in the sum of squares for the error implies an identical increase in the sum of squares for regression. All right, guys. Now this is the terminology and notation is going to get a little weird. So this might be a video that you need to. First of all, it's a video you're going to need to take really good notes on. It's also going to be a video that you may end up needing to watch a couple of times to get the notation. Notation is still kind of tricky to me. All right, let's do an example. Just to illustrate a couple of things. Let's calculate sum of squares regression. Now, what does this notation tell us? This notation tells us that we want to look at the difference in the sum squares for the regression when we add x3 to a model that includes x1 and x2. So guys, remember, this part over here is what we're adding, and this part over here is what is existing. So guys, we can do this one of two ways. We can examine the sum of squares for the error, or we can examine the sum of squares for the regression. So let's look at the sum of squares for the error first. Now the bigger sum of squares for the error is going to be the beginning, so we're going to look at the sum of squares for the error for x1, x2. And subtract out the smaller sum of squares, which will be after adding the term. Now go back to the sum of squares when we had x1 and x2 in was 109.95. And after adding x1, x2, and after adding x3 and giving us x1, x2, and x3, our sum squares for the error was 98.41. And if my mental math is correct, that's 11.54. Okay, equivalently, we can say the sum of squares for regression of adding x3 when x1 and x2 are in the model can be seen as the sum of squares for regression. Now guys, let's think about which one's the biggest. The sum of squares for regression is the biggest one. We've got all of our variables in the model. And then we'll subtract out the sum of squares for regression before we added the extra term. So guys, the sum of squares for regression when x1, x2, and x3 was in the model was 396.98. And sum squares for regression when we just had x1 and x2 in the model was 385.44. And if my mental arithmetic is correct, we can see that that also gives us 11.54. Now, where do I want to go from here? All right, let's take a look at this. This will be worthwhile. All right, guys. There may be situations where we want to add more than one variable. So let's add two variables. So guys, let's say that we have x1 in the model. And we want to add x2 and x3, given x1 in the model. So again, we can examine this one of two ways. This is going to be equal to the sum of squares for the error, which is going to be largest when we just have x1 in the model. And then we can look at the sum of squares for the error when we have x1, x2, and x3 in the model. And sum of squares, okay, so sum of squares for the error x1 was 143. And sum of squares for the error with we had all the variables in was 98.41. And that looks like it's going to be, what, 44.71? Or we could calculate sum squares regression given x1 the model by adding x2 and x3 by looking at the sum of squares for regression. Guys, remember that's going to be largest when we have everything in the model. Minus sum of squares regression when we just have x1 in the model. So it looks like 396.98. And sum squares regression 352.27. And I'm pretty sure that also gives us 44.71. So guys, at the end of the day, the notation that we have going on here is we have the sum of squares pretty much given two parts. This part right here is what we add. And it's really important that you get this early on because we're going to get into some nasty stuff in a couple of videos. And this is let's just say current. Currently in the model. So it's a notation that you've kind of seen in classes before. So we can rewrite this as sum of squares for the regression, and think about this. This is the ending sum of squares, and then the sum of squares, subtract sum of squares for regression, and this is where we begin. Which is equivalent to the sum of squares for the error, which is the biggest when we begin our initial model, and sum of squares after we've added all the variables in the model. All right, let's regroup here. Now, what I want to do next, in multiple regression, unlike simple linear regression, we obtain a variety of decompositions. It's actually pretty cool how this all will come together. But to me, when I learned this the first time, the hardest part was kind of overcoming the notation, and you can see really it's in pretty simple form. But I don't know, I struggled with that at first. So let's keep it simple. And I'll say that, relatively speaking, and examine y as predicted by x1 and x2. So, should be clear that if we have x1 only in our model, then the sum of squares total will be equal to the sum of squares regression for x1 plus the sum of squares for the error for x1. But we know the following. We know the sum of squares for regression when we add x2 into our model given x1 is going to be equal to the sum of squares of the initial model minus the sum of squares for x1 and x2. Now guys, doing just a little bit of, I'd like to solve for this. So I can see that the sum of squares error for just x1 can be rewritten as the sum of squares for the regression when we add x2 to a model that's existing with x, or that currently includes x1, plus the sum of squares for the error of x1, x2. Let me make sure I've got this right. Yeah. So I want to put this in a box because I want that to be kind of on its own. Okay. Now, so by substitution, if I put this value in here, I'm going to end up with the sum of squares for the total is going to be equal to the sum of squares for the regression on x1 plus this. Okay, now guys, this is going to play an important role, so I'm going to put flashing neon lights around this one. And I want to... Does that make it important enough? Okay. All right, so we're going to need to consider that in just a little bit. Now, so from what we just saw, in that we just saw that the sum of squares total, when we just have x1 in the model, is going to be the sum of squares for the regression with x1 plus the sum of squares for the error for x1. So it should be no surprise that the sum of squares total for x1 and x2 in our model is the sum of squares regression x1, x2 plus sum of squares for the error for x1 and x2. Now, let's see. Now, if I let's do like we just did before, and let's focus on this error term, and I can see that my sum squares for the error for x1 comma x2 is going to be the sum of squares total minus the sum of squares for the regression of x1, x2. Now guys, from earlier, we saw from this that the sum of squares of x1, x2 can be rewritten as the sum of squares for the total minus the sum of squares for the regression of x1 plus minus the sum of squares for the regression of x2 added to an existing model of x1. Now make sure that makes sense. It should. I mean, all I did was just move these to the other side. So guys, from that, and this is the primary reason I didn't want to use dosary today, because I wanted to be able to have things like this. So again, from this, I know that I can rewrite the left side as what it's equivalent to. So the sum of squares error for x1 and x2 is equal to the sum of squares total minus the sum of squares regression x1 minus the sum of squares regression when we add x2 to an existing model. And that's all we need of that. And now we've got, of course, this. Which is equal to this part. Hopefully you can see that. Okay. Well, guys, some obvious stuff happens, and we see we end up with the following. Okay, so let's let's highlight that. Shoot, my eye's itching. All right, so let's highlight that, and let's see exactly what this says. Now, my focus is on the right-hand side, so I know that we're all clever in those ways, but this is kind of my focus here. So I want to look at the sum squares regression when I have x1, x2 in the model. And so this is going to be the sum of squares for the regression of the initial model plus the sum of squares regression when we add x2 to an existing model, x1. So guys, this part right here, what would we say that? That's the contributing factor. Of x1 alone in the model. And this is obviously the contributing factor um, um, of adding x2 when x1 was already in the model. I'm sure there's a better way to state that, but you know, I think that should be pretty clear. Um, you know what I'm trying to say there, guys. One more thing that I want you to say to be aware of is that order is irrelevant. So if I have the sum of squares for the regression of x1, x2, and this should be clear, but that I can look at the sum of squares for the regression when I have x2 only in there, and this will be equal to the sum of squares of this part and the sum of squares regression when I have x2 in my model and I add x1. Now, I want to show that this is true. I don't really know how much what my video's doing right now, but anyway, I want to illustrate this for the body fat. So I want to look at the sum of squares for the regression of x1 comma x2, and I want to show that that can be the same thing as the sum of squares for the regression of x1 plus sum of squares for the regression when I have x1 in my model and I add x2. And I want to show that this is the same as the sum of squares for the regression when I just have x2 in the model plus the sum of squares for the regression when I have x1 in the model and I add x2. So I just want to show that to you. So guys, some of this is easy, and I jotted some of this down a while ago without you knowing. It's saving me a little bit. So the sum of squares for the regression when I have x1 in the model was 352.27. And the sum of squares regression when I just had x2 in my model was 381.97. Now, the sum of squares regression for adding x1 when x2 was in the model, I'm going to have to calculate that, and then I'm going to have to, let's see, this one, I've got it. This was 33.17. So we can add those two together. I don't know why in the world I don't have my calculator with me, because I hate mental arithmetic anymore. So this is going to be 1411 424.14. So I need to come up here and calculate this. I need the sum squares regression when I have, and I'm going to illustrate that. We could actually do the calculation, but I want to illustrate how we would get that using R. So let's. Well, no, wait a minute. We've got that. We've got. So given x1 in the model, when we add x2, the difference was 33.17, just as we would expect. All right, so, and again, I think that's 424.14. Well, guys, that's all I got. That's all the damage we're going to do in this video. keep me posted on how you like the change. We can always go back to the blackboard if needed, but I think for obvious reasons this was pretty effective for this video. So, guys, that's all I got. Take care.